Oh my God. Whoa, wait, whoa. Oh, this one. All right, we're going to calculate the Maclaurin polynomial for tan inverse. Find a bound for the error, verify the result. Okay, so let me ask, because we kind of have three parts. So as far as T3 of 1/2, any questions about that? I'm guessing the questions were about the error bound. Error. The word error just is a weird word. If you say error over and over again, it just sounds like error. Right? It sounds weird, doesn't it? All right, so as far as the bound goes, the error bound, so we have it kind of here. Actually, I can scroll up a little bit. We need the graph for this. So remember, in the formula for error bound, we have that k in there. And the k is based on this. And so this is where the graph is going to help us. Now, remember, the whole idea with like doing a Taylor polynomial in the first place is that you don't have, like, we don't have the actual values of all these things. We don't have a way of computing it. We're doing it by hand or with a very rudimentary device or whatever. So anyway, as far as the max value of this is where we're going to go ahead and use the graph. And this is the graph of the thing that we're trying to find the max value of. So we can use 5. Now notice it's actually a little less than 5. And so yeah, you could refine the error bound a little bit more by trying to figure out exactly what decimal place that maximum value is at, or just use 5. If you actually were to calculate it with the 5 or the 4 point, whatever that is, you'll find it actually doesn't change the error bound significantly. It's good enough. And so, yeah, we're going to use 5 for k. Because it definitely doesn't go above 5, does it? So that's the key for finding the error bound. And then you plug it into the formula. And then there's the formula there. Which is that. So any questions about that? Yes?
Could you give like a really quick refresher on like what k is? Because I wrote it down. I don't really understand it.
So in this case, we're finding the third degree Taylor polynomial. So n is 3. So you go to the next derivative, the fourth derivative. And it's the maximum value that derivative is going to take between x and a. So a is the value you're centered around, x is the value you're approximating. K? Get it? Get it? Y'all aren't laughing. There you go. Yeah, so in this case, we were approximating at 1/2, and it was a Maclaurin, so it's centered around 0, so we're looking between 0 and 1/2. Any other questions? But seriously, did that answer your question, Karen?
Yes.
Okay. Any other? Yes. I'm afraid I'm going to remember wrong. That is important. I will be honest. Any other questions while I'm looking this up? Oh, it should include the absolute value. Some words hard. Yes, absolute value. K should be the maximum value that the absolute value of the n plus 1th derivative takes. Any other questions? All right. Oh, yes, Sid?
So finding K, we can use like the
Yeah, well, are you talking about like to find an absolute maximum?
yeah.
Yeah, although like also here's another thing that we didn't talk about. Think about sine and cosine. So if you're actually trying to approximate sine or cosine somewhere and then trying to find the error bound. So we know that the derivatives of sine and cosine just go back and forth between sine and cosine. So what do you think a convenient value to use for k would be? A good enough convenient value? Exactly, 1. Because we know that the derivative of sine or cosine is always going to be some flavor of sine or cosine, and then the maximum value that's going to take is 1. And that's really nice to work with. And it, again, is good enough. Yes?
So in general, we can just approximate k.
Yeah, you don't have to, I mean, obviously if you have some sort of tool like a calculator handy and you want to get a really precise value for k, to get a really, really precise value for error bound. But like I said, if you tried putting it in with the actual maximum, I can't remember if they give us, oh, they did. Yeah, I wrote it down. So since we have our calculators, we could use our calculators to find the a good decimal approximation for this maximum value. If you recalculated the error bound, it just doesn't make that much of a difference. So, alrighty, well, let me have your homework. And hey, look at this! I thought we weren't going to have these. Yeah, well, we'll talk about that. I'll pause the video right now. I'm going to pause. Bye-bye if you're watching this. You can. I'm waving at you right now, but you can't see. Ah! All right, number 2.
I don't even know why I said that.
Any questions on this one? Anybody one more time looking at this one? Number 3. I think I can't quite put 4. There's 3. Any questions about number 3? Hey, boo boo. Yogi Bear is smarter than the average bear. That's all I know of the song. Anybody one more time looking at this one? Then for the grand finale. Any questions at all? Oh. For fantastic.
For 50%.
Oh.
I
I got nothing. All right. Today's going to be fairly light. So enjoy it while it lasts. All right. I can't believe it's already January 13th. 2022. What the heck? I remember when we changed to the 2000s. And the Y2k bug. Ooh, that was scary. Have you heard about the Y2k bug? So they were really worried because all the computers, well, not all of them, but a vast majority of computer systems, even like major ones like banking and stuff, all of the programming had been written to only have 2 digits for the year. So when we switched from 1999 to 2000, it was going to go to 0, 0.
Why did they not just think of that like 5 years ago?
Well, because it seemed like 2000 was so far away. So then they were all worried about like, whoa, what about in the year 2000 then? Are these systems going to crash? Is the global economy going to crash? Is it, oh my God, it was scary. What was going to happen? You know what happened? Absolutely nothing. Now, granted, they did do a lot of work between like when it started coming up to the actual turn of the millennium that, oh my God, this could be a big deal. But yeah, absolutely nothing happened. But, I mean, they thought that power grids were going to totally collapse and the economy would collapse. People might lose money that they had invested because systems would crash. Yeah. There's actually a movie called Entrapment with Catherine Zeta-Jones and Sean Connery, and they play thieves, but they make use of the year 2000 bug to try to get some of try to make their heist. Anyway, there you go. Year 2000. No big deal. What are we doing? Oh, right. Section 9.1. And section 9.1 is solving, I forget the actual title. I was going to call it solving differential equations because that's really what it is. Now, this year, we are going to stay rather light. Actually, what's on the AP exam is not bad with solving differential equations. In fact, you probably already know this, but we're still going to cover it. But you can actually take a whole class in college called Differential Equations, DiffEQs, and it's like one of the harder. It's like right up there with organic chemistry as far as like people's fear of the class. I never took OChem, so I don't know. But anyway, what we're gonna do, not too bad. So the notes part, not so bad. Then we're gonna do 3 examples. And that's it. In fact, this is it right here. This is what we're covering. Yeah. Okay. So the order, just a little vocabulary. When we talk about the order of a differential equation, it's kind of like talking about the degree of a polynomial, but we don't call it degree, we call it order. And so if the degree of a polynomial is the biggest exponent on the variable, then the order of a differential equation is the highest derivative. In the equation. We're sticking with first order differential equations, where the biggest derivative is 1, the first derivative. But you can have differential equations with second, third, fourth derivatives in them. So the topic for today specifically is called, I'm going to go purple, separable first order. It's the first order. Separable first order differential equations. Dun, dun, dun. And separable first order differential equations, just fun to say, are ones that look like this, where we can say that dy dx is equal to f of x times g of y. That's a y. Almost looks like an x. Let me fix that. That's a y. So the separable is because we can separate the variables. And then if you can separate the variables, then the idea behind solving them is super easy. So there you go. That's really the end of the notes. Now we're just going to go into examples. Wow, this is nice. So for the first example, we're actually not going to do a first order differential equation. I kind of lied. We're going to do a second order. But we're not really going to solve it. Here's what it is. We're going to show that y equals 4x to the fourth minus 12x squared plus 3 is a solution to y double prime minus 2xy prime plus 8y equals 0. What does this mean? I don't get it. This is stupid. Anybody know what it means? Joshua? You're on the right track. Yeah, but what do you mean by derive one in an equation? I can't even say it. Derive one equation into another. There we go. Yeah. That's pretty much it. What we're going to do is we're going to take this guy that I'm highlighting in blue. And we're going to find the first derivative and the second derivative of it. And we're going to plug it in here. And then we should get 0. That's all. So let's see. Does this work? Maybe it doesn't. I don't know. All right. If y is that, this is just polynomial. This is easy. Y prime is 16x cubed minus 24x. Y double prime is 48x squared minus 24. Nose itches. And I'm going to see how many colors we can use today. So then I'm going to take this differential equation, which is a second order differential equation because the highest derivative is 2. And we're just going to plug in. That's all. Yes. Well, we're not going to solve anything higher than a first order. All right, so y double prime is 48x squared minus 24 minus 2x times y prime, which is 16x cubed minus 24x. And then plus 8y. Was this really going to equal 0? It doesn't look like it, huh? Is this equaling 0? Yeah. Don't forget. What else can I plug in? Y. It's actually, I mean, it may seem silly, but it's one of those things where I see that a lot where people are like, it's not working, it's not working. Well, wait. You didn't plug in everything. Plug in the Y. Might as well since I got here instead of erasing. We got those. Well, that's pretty much all that cancels so far. I could have plugged in the Y back then, but, you know. Then I can't make my point. Anyway, y is, where is it? 4x to the fourth minus 12x squared plus 3. Oh my god, I'm so excited. 32x to the, ooh, that's going to cancel. Oh, I must have forgotten to write something down from above. Can't do multiplication. Where did I mess up? Because I did mess up somewhere. Oh, there we go. See? Silly mistakes. Silly. Don't tell anybody. You people watching on the internet. That one I did not do on purpose. I'll put it over here. 96x squared, 96x squared. Now Everything cancels. Oh my gosh, it's very exciting. So, there you go. That's all you got to do. So, any questions about that one? Yes.
Are there multiple solutions to that differential equation, or is it just that one?
That is an excellent... Boy, words are hard. That is an excellent question. What do you guys think about that? So, in case you didn't hear it, the question was, are there multiple solutions to this differential equation, or is this the only solution? Yeah.
There are multiple, because if you implicitly integrate the differential equation, it'll give you like plus c.
Yeah. So I actually can't answer that question specifically, but in general, what Karen just said was right. In general, differential equations do have multiple solutions because of that plus c. It may be that this particular one is special and it just happens to only have one, but in general, they do have multiple ones.
Okay, and is it like multiple specific ones, or if it's plus c, is it just like, yeah, an
Infinite number. Yeah.
Okay.
Which is going to bring us to some other tiny vocabulary, which you guys have heard before, but the particular versus general solution. So, any other questions? All right. So, then speaking of that, our next example, now let's actually solve. Hey, stop it. Find the general solution to dy dx equals 6x squared plus 2y plus cosine y. Dun, dun, dun. So remember, the general solution, that's where we're going to have this plus c that we keep talking about. We'll see, in case you're like, I don't know what you're talking about with the plus. You'll see it in a moment. And then the second part to this question is going to be to find a particular solution, meaning find the actual value for c for a particular situation. Let's just do this one first. Let me get a new page so I can. There we go. So just in, like, this one's pretty easy to see how we can get all the y's on one side and all the x's on the other. But sometimes it's a little harder to see how to separate the variables. So in general, remember how I wrote this up above? So in general, if you take your, put your derivative on one side, and then on the right-hand side, separate the x's and the y's. And I know that may seem silly, but sometimes it's just not obvious, like everything's all jumbled and it becomes harder. So get your derivative by itself, and then on the other side, separate the x's and y's. And then the idea is we'll put the g of, should put that in front. We'll put the g of y on the left with the dy, and then we'll put the f of x on the right with the dx, and then you can integrate and you go from there. So that's the idea behind it. So let's do it. Yay. Let's use this color now. All right, so we can see that all those y's in the denominator, we can just multiply by that denominator, put them on the left-hand side, and that puts the x's and the y's separate. So it is going to be 2y plus cosine, 2y plus cosine y dy equals 6x squared dx. We have now separated the variables. And then we can integrate both sides. It's like magic. So we'll get y squared plus sine y plus c equals 2x cubed. Oh, plus c. But wait a minute. Are those c's equal to each other? Yeah, not necessarily. But I can combine them. Remember, they're just arbitrary constants. So if I combine them to a new c, we can put the c's on one side. And so you probably remember that's what we typically do when we are solving differential equations. We don't put a plus c on both sides and then combine. It's always going to happen. Just put the plus c on the side with the x. Because most of the time we're going to try to solve for y. Although, can we solve this guy for y? Yeah, so we're going to leave it like that. There's my general solution right there. In fact, I don't even need that cube. It's okay if you put that subscript of 3 on there. We don't need it. There's my general solution. Any questions about the general solution? All right. So the general solution is that plus c, but then we're going to find the particular solution. I'm not going to have enough room. I'm not even going to try to squeeze it. So then we're going to find the particular solution for y of 0 equals 2. So then you just plug in and solve for c. Ain't no big thing but a chicken wing. Chicken wings actually sound good. Alright. So y is 2, so we have 4 plus sine of 2 equals x is 0. So that's just going to be c. There's c. See? Tough crowd today. So there it is. Yeah, all right. So y squared plus sine y equals 2x cubed plus c, which now we know is 4 plus the sine of 2. Is there anything we can combine to at least simplify this thing? No. So that's it. There is our particular solution. Sometimes you can solve for y. The general and particular solutions are quite lovely, and sometimes they're another type of quite lovely. So there you go. Any questions about that? Oh man, we've only got one more question left. There you go. That's what I wanted to hear. Ah! All right, last one. You guys try this one. Solve. Now, if it doesn't say anything like, well, anyway, let me read the whole thing. Solve y prime equals x squared y. So if it doesn't say anything about particular or general, then look, does it give you anything to find the particular solution?
No.
So you just are going to find the general solution. Go! It's a race. It's not really a race. I shall pause. I shall freeze. And I shall pause the video. Goodbye, people. Hey! Look at that! So, one little note and then we'll be done. I put these little subscripts on the C to show you as we're going throughout that all these C's are technically different values. But technically, I mean, actually I should say technically you should have it because they really are different values. But you will often see when people are solving these, they don't put the subscripts in. It's kind of a, some people do, some people don't. I'm not going to take off if you don't. But you really can't drop the absolute value until you get down to this point. So the absolute value of some arbitrary constant times e to the power, well, that arbitrary constant then is a plus or minus arbitrary constant. So. Yes?
If you try to make this into a particular solution, would you have to go all the way back up to the top and solve for C1?
Ooh. That is an excellent question, but I don't know how many people actually heard that question. I don't know actually if even the video people heard it. Did you guys hear it?
No.
Answer me! God, they're so rude online. It's fine, whatever. They're like, who's she talking to? Anyway, so the question is a good question. The question is, done. The question is, should you, like if you had to solve for a particular solution, do you have to go back here to plug in? Do you go here? Like, where do you go to plug in to find C? What's the answer? Yeah, you at any point you can plug in. You're going to get the same final answer, so you choose. Whatever seems easiest to you. Or whenever you remember, shoot, I'm supposed to do these. Any other questions? That's it. We're done. Goodbye. Goodbye, online. Oh, thank you very much. You hear that?